Okay, let's get started today's my presentation. Hello, my name is Jungi Jang. Today I will introduce our paper DPar2 Fast and Scalable PARAFAC2 Decomposition for Irregular Dense Tensors, which is published in ICDE 2022. This paper received Best Research Paper Award honorable mention. This is a joint work with my advisor, Professor Yu Kang. First, let me give you a research question. Given an irregular dense tensor, how can you efficiently analyze the tensor? As shown in the figure, an irregular tensor is a collection of matrices whose columns have the same size but rows have different size. The answer is to exploit DPar2, which is a fast and scalable tensor decomposition method to efficiently analyze the tensor. It is today's outline. I describe introduction, proposed method, experiment, and conclusion in order. Many real-world data can be represented as irregular dense tensors, which is a collection of matrices whose columns have the same size but rows have different sizes. For example, stock data can be represented as an irregular tensor. Each stock can be represented as a matrix whose rows and columns correspond to time and feature respectively. Note that features can include opening price, trading volume, and technical indicators. Then an irregular tensor consists of several stocks whose listing periods are different from each other, but have the same number of features. In addition, sensor data and music data can be also represented as irregular tensors. Then given an irregular tensor, how can you analyze it? PARAFAC2 decomposition is a fundamental tool to analyze the tensor. Recently, it has been repopularized for analysis of it. Formally, PARAFAC2 decomposition finds 4 types of vector matrices which approximate a given tensor well. Note that we call a matrix xk a slice matrix. As shown in the figure, each slice matrix is decomposed into qk, h, sk, and v transpose. Note that h and v are shared vector matrices across all the slice matrices. Vector matrices of PARAFAC2 decomposition can be used for many real-world applications, including dimensionality reduction, anomaly detection, trend analysis, and phenotype discovery. For example, given stock data consisting of time, feature, and stock, we can analyze correlations between features or find similar stocks in stock data. Then how can you find the vector matrices of PARAFAC2 decomposition? Alternating least square is widely used for obtaining vector matrices. It iteratively updates a vector matrix while fixing all other vector matrices. But the main problem of ALS is to require heavy computational cost due to since there are computations involved with a given tensor at each iteration. For example, ALS needs computations between a tensor and vector matrices for all k at each iteration, and its computational cost is proportional to the size of the given tensor. So the limitation of previous PARAFAC2 decomposition methods are that they fail to efficiently handle an irregular tensor due to the computations involved with the tensor as described in the previous slide. In addition, there is a room for improvement of employing multi-core parallelism. Therefore, we should make PARAFAC2 decomposition faster and more scalable to analyze large-scale irregular tensors. Now I introduce our proposed method, DPar2. We propose DPar2, which is a fast and scalable PARAFAC2 decomposition method for irregular dense tensors. We devise our proposed method by exploiting 3 ideas. The first idea is to compress a given tensor using randomized SVD. With this idea, we handle small compressed data instead of the large tensor, improving efficiency of updating vector matrices. The second idea is careful reordering of computations with compressed results. Although we obtained small compressed results, naive computations cannot lead to minimizing computational costs and avoiding generation of large intermediate data. We should carefully determine the order of computations. And the last idea is to carefully distribute works between threads by considering various lengths of matrices. Now I describe our proposed method in more detail. First, we compress a given tensor before iterations. The compression is performed only once before iterations, and only the compressed results are used at iterations. Note that the results are much smaller than the given tensor. There are two compression stages. In the first stage, we compress each slice matrix xk using randomized SVD, which enable us to efficiently compress matrices with low errors. And the second stage further compresses the intermediate data obtained at the first stage. This slide describes the detail of the compression step of DPar2. In the first stage, each slice matrix is decomposed into AK, BK, CK transpose using randomized SVD. In the second stage, we construct a matrix M by horizontally concatenating CK, BK that are obtained at the first stage. Then we decompose a matrix M into DEF transpose using randomized SVD. Finally, we can express the relation between the final output of the decomposition and a slice matrix. AK, FK, ED transpose is approximately equal to XK. Note that each slice matrix has AK and FK, while E and D are shared vector matrices across all the slice matrices. Thanks to the two-stage compression, we efficiently obtain the compression results much smaller than an input tensor, and it lays the groundwork for efficient updates. Now I will show you how we update the vector matrices using the compressed results. Naive approach would update vector matrices after reconstructing slice matrices from the compressed results. However, it requires high computational costs and generates large intermediate data due to the reconstructed one whose size is equal to an input tensor. Therefore, we need careful reordering of the computations with the compressed results to minimize costs. First, we update QK using the compressed results. In contrast to naive computations, our update for QK avoids reconstruction and redundant computations for AK by exploiting the property of AK. Thanks to it, we fully exclude computations involved with AK so that we efficiently update vector matrices QK. Then we update the vector matrices H, SK, and V. By using factorized matrices and carefully reordering of computations, we also reduce the computational cost and avoid generating large intermediate data. Equations for updating vector matrices are quite complicated, so we provide an example figures for a comparison between naive computations and our proposed computations. As shown in the figure, a naive computation includes matrix multiplications between large matrices, while our computations include matrix summation and matrix multiplications between small matrices. Our final challenge is to maximize multi-core parallelism for PARAFAC2 decomposition. Given an irregular tensor, the number of rows of slice matrices is different. For example, stocks have different time lengths and thus row size are quite different. Since this difference affects computational costs related to slice matrices, so we need to consider it to minimize computational cost on multi-core systems. So our idea is careful distribution of works between threads to address the challenges. DPar2 distributes slice matrices fairly across each thread by considering their row size. So to reduce the completion time, DPar2 makes the sums of rows of slices processed by threads be nearly equal to each other. Now let's move on to experimental sections. We answered the following two questions in the experimental section. The first question is about performance. How quickly and accurately does DPar2 decompose a given tensor compared to other methods? The second is about scalability. How well does DPar2 scale up with respect to tensor size and target rank? And how much does the number of threads affect the learning time of DPar2? We use 8 real-world irregular tensors, including sound data, stock data, and traffic data. Each slice matrix has different IK, and J is the size of the common axis, and K is the number of slice matrices. We compare DPar2 with 3 existing Preprocessing decomposition methods for irregular tensors: PARAFAC2 ALS, RDALS, and Spartan. We use a metric, fitness, which measures how a model approximates a given input tensor well. Fitness close to 1 indicates that this model approximates a tensor well. The first experiment is about trade-off between running time and fitness on 8 real-world tensors. We measure running time and fitness for 3 target rank, 10, 15, and 20. As shown in the figures, DPar2 outperforms existing method, providing up to 6 times faster than competitors, while having comparable fitness. Now I examine pre-processing time and iteration time on tensors. For the pre-processing time, we compare DPar2 with RDALS, since only DPar2 and RDALS have a pre-processing step. As shown in the figure, DPar2 is up to 10 times faster than RDALS. Specifically, for FMA and urban dataset, which are 2 largest tensors, DPar2 has much lower pre-processing time than RDALS because RDALS cannot avoid the overhead to handle the large tensors. For the iteration time, DPar2 is up to 10 times faster than competitors since our method handles much smaller compressed data than the competitors. Now we evaluate scalability in terms of tensor size, rank, and number of threads on synthetic irregular tensors. Note that tensor size and rank are related to size of an input tensor and size of an output tensor, respectively. So the first 2 figures show that DPar2 is more scalable than other Preprocessing decomposition method in terms of both tensor size and rank. And also, DPar2 gives near linear machine scalability as shown in the last figure. Now I conclude this presentation. We propose DPar2, which is a fast and scalable Preprocessing decomposition method for irregular dense tensors. We experimentally show that DPar2 outperforms existing Preprocessing decomposition method, and we find interesting patterns in real-world irregular tensors using DPar2. Thank you for listening. It is the end of this presentation.